Our task for today is to place the following compounds in order of increasing boiling point. The 5 compounds of interest are propanol, propan-1-ol, propane, 1-chloropropane, and propanoic acid. But before we start ordering these 5 compounds, we need to understand the factors which impact their boiling points, which are their molecular weight, their contact area, and the intermolecular forces. Molecular weight simply refers to the size of a molecule. So if we take a look at an example, hexane versus butane, hexane has the higher boiling point as its molecular weight is higher. Taking a look at contact area simply refers to the area in which molecules are in contact. So if we consider the previous example that I just spoke about, I am coloring the contact area in blue. And as you can see, the blue line in between hexane molecules is longer than in butane molecules. So the contact area in hexane molecules will be higher. And as a result of that, the boiling point of hexane molecules will also be higher. And the main focus for today, which are intermolecular forces, are just forces that occur between molecules. This force in this diagram specifically here between two water molecules is a hydrogen bond. And yeah, let's take a look at some of the different intermolecular forces. So the 5 different types of intermolecular forces are ion-ion interactions, ion-dipole interactions, hydrogen bonding, dipole-dipole interactions, and van der Waals forces. The three weakest forces, hydrogen bonding, dipole-dipole interactions, and van der Waals forces, are going to be the forces which we are going to be using to explain the order of boiling point of the 5 compounds that we looked at earlier. And the arrows are just pointing to what these forces would look like. So hydrogen bonding, as we spoke about earlier, is it's just hydrogen bonded to nitrogen, oxygen, or fluorine. And yeah, that's a hydrogen bond. And then looking at dipole-dipole interactions are the interaction between a partial negative end of a molecule and a partial positive end of a molecule. And van der Waals forces is just an uneven distribution of electrons that induce a partial negative and partial positive end in an atom. Moving on, let's start taking a look at some of the molecules that we have. Propanol is a polar molecule with a formal group that I am circling in red. It is a C double bond O group, and in the oxygen of this group carries a partial negative charge, and the carbon carries a partial positive charge. And when you have two propanol molecules, the partial negative end of the molecule will interact with the partial positive part, which is just between the oxygen and the carbon. This forms a dipole-dipole interaction, and van der Waals forces can also occur between propanol molecules. Taking a look at propanol, propanol is also a polar molecule because of the hydroxyl group at the end. And because of this hydroxyl group, which is unlike the formal group that we previously spoke about, this functional group has a hydrogen in it, which allows alcohols to have hydrogen bonding capabilities. For example, here, a hydrogen bond is shown between two propanol molecules between the partial negative oxygen and the partial positive hydrogen of two molecules. Taking a look at propane, propane is the only nonpolar molecule of the 5 compounds of interest. This is because the carbon-hydrogen bonds the electronegativity of those bonds are negligible, so we describe the overall molecule to be nonpolar, and the only intermolecular force that can occur between propane molecules is van der Waals forces. Taking a look at 1-chloropropane, 1-chloropropane is also a polar molecule because of the chlorine atom in the carbon chain. And this chlorine atom allows for dipole-dipole interactions and van der Waals forces. And the dipole-dipole interactions occur between the partial negative chlorine atom and the partial positive carbon atom. And our final compound of interest is propanoic acid. Propanoic acid is also a polar molecule, and that is a result of the carboxyl group, which is this group right here. This allows for hydrogen bonding, dipole-dipole interactions, and van der Waals forces. In this diagram here, we show the hydrogen bonding interactions that can happen between two propanoic acid molecules. To sum it all up, we are going to categorize the compounds that we are given into the type of intermolecular forces that can occur. So propane is the only compound in which can only form van der Waals forces. So we know that propane has the lowest boiling point because if it's only capable to form van der Waals forces, which is the weakest intermolecular force, then its boiling point will be relatively low. Taking a look at propanol and 1-chloropropane, they are both capable of forming dipole-dipole interactions and van der Waals forces. And taking a look at propanol and propanoic acid, they are capable of forming hydrogen bonds, dipole-dipole interactions, and van der Waals forces. So how can we determine which of these two molecules in these two groups have a higher boiling point? Let's take a look at propanol and 1-chloropropane first. We can compare the electronegativity difference of the um, the groups which make the overall molecule polar. For example, in the aldehyde or propanol, the C double bond O group or the formyl group is what makes the aldehyde polar, and the electronegativity difference between the oxygen and the carbon is about 0.89, and the electronegativity between the carbon-chlorine bond is about 0.61. Because the electronegativity difference is greater in the aldehyde than in the haloalkane, we know that in the aldehyde, stronger dipole-dipole interactions exist, which means that the boiling point of aldehydes must be greater than the boiling point of haloalkanes. And taking a look at propanol and propanoic acid, we can see, we can determine which of these two have the higher boiling point by how they hydrogen bond. So alcohols will hydrogen bond in this manner, as we see on the left, whereas propanoic acid will hydrogen bond in a sort of diamond shape. And this diamond shape makes the compound more stable. And because it is more stable, we will have to give the propanoic acid more thermal energy to reach its boiling point, which is higher than that of the alcohol. So now we can put everything we know all together and order the 5 compounds from lowest boiling point to highest boiling point, which is as follows.